Hello everyone. Today I'm going to share my understanding on paperclip and contrastive learning. What was the motivation behind selecting this paper and the topic? What particularly drew me to this topic was how CLIP demonstrated that models can develop robust visual concept understanding through natural language supervision, potentially bypassing any supervision bottlenecks. This approach offers promising directions for creating more flexible AI systems that can generalize to new tasks without explicit training. Then historical perspective. We have seen papers like frameworks like SimCLR in which we learn representations for the images through maximizing the alignment between two different augmented views of the same image. Then we have also seen many other examples of contrastive learning where we want to try to make similar spreads closer to each other. Then the important point that this paper highlights is the power of the NLP. What this point is trying to say is that natural language is used as a flexible supervision signal. So the flexibility of natural language as a supervision signal represents one of the most powerful clips significant innovations. Let me elaborate this point more to get what I'm trying to say. Whenever we have traditional classification labels, the problem that we face that it requires extensive manual labeling as well as it limits our model to recognize only predefined classes, and the model struggles with different distinctions or overlapping concepts. Then the this natural language supervision also helps us to capture semantic relationships. By this I mean that language naturally encodes semantic relationships between concepts. Consider these examples where we have a label, say a rusty vintage image containing a bicycle. So this whole sentence is a supervision signal, but which a traditional model won't be able to capture. But our clip models implicitly learns that the bicycle, cycle, and bike refer to the same object, and what is the visual difference between vintage and modern objects. Then moving on, the clip models also learns cultural and contextual knowledge. By this I mean text descriptions often contain cultural references, which contains metaphors and some contextual information that is needed to be learned by our model. Clip learns all this by learning by some process that I'm going to elaborate in the upcoming slides. Through these descriptions, Clip develops association between visual patterns and cultural concepts, enabling it to learn, understand images at a more conceptual level. What is contrastive learning? The basic idea of contrastive learning is explained through this image. As you can see, two bears with different images, but they will lie in the same embedding space in the closer proximity of each other in the embedding space, where two different animals, say otter and bear, will lie far apart in the embedding space. So this is the basic idea of contrastive learning. Let's move on. What is the contrastive objective and unified embedding space? The contrastive objective is the mathematical foundation that powers Clip's ability to connect text and images in a meaningful way. So, the what this unified embedding space provides us with different strong features. These features are semantic proximity is it should be equal to geometric proximity. By this I mean the contrastive objective enforces a critical property. Items with a similar meaning should end up positioned close to each other in that space, whereas the items with dissimilar concepts should remain far apart. This is done for both image and text. For example, an image of a cat and the text, say the photograph of a cat, should lie closer to each other in the embedding space. Then it also provides the cross modal alignment. The true power comes from how this objective aligns the two modalities. Consider what happens during training. Clip processes a batch containing multiple image text pairs. for each image, its embedding is paired with the closest text embedding, and for each text, its embedding is paired with the closest text embedding. Then we also want this to be true for the all other image text pairs. Then let's talk something about mathematical implementation. So the contrastive objective is typically implemented using a temperature scaled symmetric cross entropy laws. So for this, what do we have? We have a batch of n text image pairs. So for each image text pair, we compute similarity scores between all possible n cross n image text combination. Then for each image, the loss increases high similarity with its pair text and low similarity with the other text. This is true for each text also. Then the symmetric world comes because we take the average of the loss from each text and the loss from the each image. So this, there is a loss contribution from both image embedding and text embedding. Then the temperature parameters control how strictly the model enforces these constraints, balancing between perfect discrimination and generalization ability. So what are the data sets they have used? So for training, they collected a data set from the publicly available data, that is internet. So they queried for each label. They did millions of queries and collected a total of 400 million image text pairs from the internet. These pairs were not manually labeled. Then the dataset is not publicly available, but it is a well designed and general dataset covering a wide range of visual concepts and categories. Now let's talk about evaluation dataset. So clip is evaluated across 30 plus publicly available benchmarks. So for example, consider for image classification, its performance is evaluated on the ImageNet dataset. For sketch recognition task, is the performance is evaluated on the dataset named sketch. Then the training process. So the training part comprises the clip contains two main components: the image encoder and the text encoder. For image encoder, they use ResNet 50 or transformers. For text encoder, they mainly use transformer models similar to GPT. And when during training, the surprising part was the very large. They use a very large mini batch of size 32,768. So both encoders map their respective modalities into a shared embedding space, and as I told you earlier, then the similarity is calculated between every possible pair. So let's highlight another important fact that clips enable us to have is zero shot classification. So what basically is zero shot classification? Zero shot classification refers to classifying or making model prediction without any actual training. So let's see how we can do zero shot classification. To classify an image into one of the several classes, we convert each class into a text. So for example, say the class was cat, so we can have a text called the photograph of a cat. Then we embed both the image and all text class text into a shared space. We measure the similarity between the image embedding and the each class embedding. Then the class with the highest similarity is the prediction. So this is how zero shot classification is done. Then there are various properties that clip also provides. So first one is the analogical reasoning. Second was the transfer between modalities, and then we also discuss how powerful is zero shot clip against all other models. This we will see in a bit. So let's move on to the coding demonstration and do performance analysis of clip. So as you can see here, so this figure shows the performance analysis of clip with various other models. So as you can see, zero shot clip outperforms ImageNet's SimCLR version 2 as well as ResNet. It is way better than ResNet 15. The linear probe clip, the where we train the last embedding layer for that particular data, performs better than zero shot clip. But we can see zero shot clip still performs better than SimCLR and ResNet. Then move let's move on to the coding demonstration. So for coding demonstration, I tried to create a miniature version of the clip. For this I used a dataset called flickr 8K. In this dataset there are 8000 images and corresponding 5 captions available for each image. So what I have done is that I have created a dataset in which I randomly selected uh, for each image the for each image I have randomly selected. So for what I have did is that for each image I have randomly selected a label out of the 5 available captions. Then what I have done is I have used the bulk transformer for image for text encoder and for resnet 18 for image encoder. Then this is a small example of tokenization where we give the sentence hello world and we do padding with zeros and the max length of the encoding vector is 10. For this example I have considered, whereas in true example the max length of the encoding vector is 32. So what it does is we get a input id and embedding vector. This is the first vector and the second one is the attention marks. So this attention marks tells us that what are the original embedding values in the vector and what are the padded values. So 1 1 1 in the first four places says that these there are 4 values corresponding to the true and others are padded values. Then this is the visualization, the 5 levels with their corresponding image. Then what I did was then this I used as I told before, I used resonate 80 for image encoder and BERT transformer for text encoder. Then the clip model trains a embedding uh, embedding model which embeds the text encoding and image encoding into a common embedding space, so that the size of the common embedding space was 256. The main idea was that not to train the you- to use transfer learning. So we I used the pre-trained weights of ImageNet and BERT, but what I trained was the this embedding metrics. Then first I was curious to see the performance on pre-trained weights without any training. So the performance was not that good. Then I trained the model for 30 pox. Basically, I trained that embedding matrix or that transformation matrix into that transform into a common embedding space. So for 30 pops, then I evaluated on the training dataset, testing dataset. Sorry. So the original dataset was split into 2 parts. 80% was the training data and 20% was the testing data. So as you can see, the top 1% accuracy is 52%, which is not bad. As for each image, we have the 5 corresponding captions, so this accuracy is good. Then what we observed that we get a good accuracy even when training on this small data set. Then now I tried to increase the batch size to uh, train on the complete data in one go. So I did that for 10 epochs. Then we see that the accuracy decreases. This was surprising, but which explains that the model can be learning some more semantic uh, relationships, leading to low accuracy because of the random selection of the image labels. Then what I did was I evaluated the model for top 5 accuracy, and we get what we expected. So we get a good accuracy of 82% because the model is learning some semantic relationships, though not that clear ones. Then we try to compare our performance with the clip model. That was the main approach of this clip miniature clip version. So, as was expected, the clip performs very well and gets 100% accuracy. This was expected because the clip was trained on a very large data set, and this is a very small data set. So, I have used the whole training data set for testing on clip because the 8000 images is a very small data set for clip. Then let's talk about some reflection and what uh, I found surprising about this clip model. So the most surprising aspect of Clip was its remarkable robustness to distribution shifts. And what can be the scope for improvement? So the model shows limitation in fine-grained recognition tasks, suggesting that the general language description might not always capture subtle visual distinctions. So, for example, as we have seen in the research paper, the clip models does not perform on non-general data. So, for example, say MRI image classification. So they also show that it performs worse on MRI images, because that is not general data, that is not available for on internet easily. So we need to work on that aspect. So developing methods to enhance detailed understanding without losing generalizability to represent an important field is also a research direction. Thank you. That's all from my side. Thank you.